Okay, we're going to start with some oldies but goodies. Okay. Shh. All right, some oldies but goodies. We've already seen these, but it doesn't hurt to remind you. Only write down the ones that you need to that aren't fresh and familiar in your memory. So first of all, they're using a different angle measure instead of theta or beta or alpha or omega. They're using U for some reason. And they're saying that we should already know the reciprocal identities. You're comfortable and familiar with those, so I wouldn't write them down. Sine of u is the equivalent of 1 over the cosecant of u. Cosine u, 1 over the secant. The tangent of u is 1 over the cotangent. Cosecant is 1 over the sine. Secant of u is 1 over the cosine of u, and so forth. Quotient identities. This one, I think many of you probably recall. I saw some of you using it on your test, and that's good. The tangent is the same thing as the sine over the cosine. So if we have a tangent of some angle, we take the sine of that angle over the cosine of that angle, and we'll simplify it to figure out what the tangent is. Likewise, the cotangent is the same as the cosine over the sine. Okay, so those aren't anything that's earth-shattering. You've used those all last chapter. Pythagorean identities was one that I introduced to you, and I said if you don't get this, that's okay. You can always build your triangle and work your way around it, but now it's going to be used. So sine squared of an angle plus the cosine squared of an angle is going to be equal to 1. If you can remember sine squared of an angle plus cosine squared of an angle equals 1, you can derive the other two from it. Because if I divide sine squared by itself, sine squared of u divided by sine squared of u, I'm going to get a 1. If I do that, though, I have to divide every single term by sine squared. So if I divide cosine squared by sine squared, I'm going to get cotangent, sorry. Cosine over sine is cotangent. And then if I divide 1 by sine squared, 1 over sine squared is cosecant squared. Okay. I can derive the other one as well by dividing sine squared and cosine squared and 1 by cosine squared. So when I divide sine squared by cosine squared, sine squared over cosine squared is tangent squared. Cosine squared over itself is 1, and 1 over cosine squared is secant squared. So if you remember 1, you can get the other two. Okay. Cofunction identities. What does the co in cosine mean? It is the cofunction of sine, which means co for complementary. Okay. So whatever the sine of an angle is, the cosine of 90 minus that angle is going to have the same value as the sine of the original angle. They're 90-degree separation, complementary, co for complementary. And in pre-calc, we write that as pi over 2. So if I know the sine of pi over 2 minus u is going to have the same value as cosine of u. The cosine of pi over 2 minus u is the same as the sine of u. The tangent of pi over 2 minus u will be the cotangent of u. And its cofunction, the cotangent of 90 minus pi over 2 minus u, is going to be the tangent of u. And secant and cosecant are cofunctions. So the secant of pi over 2 minus u is the cosecant of u. And the cosecant of pi over 2 minus u is the secant of u. Remind me, what's an even and an odd function? What do their graphs look like? Parabolas are even functions, okay? So what is unique about parabolas in their native position when they haven't been shifted? And they're symmetric about the y-axis, okay? And even functions, all even functions are symmetric about the y-axis, okay? Odd functions is like y equals x cubed, right? Or John Travolta, Saturday Night Fever kind of look. So what was it symmetric about? No, the single point, 0, 0, the origin, okay? Why the odd functions are always symmetric about the origin. So is sine odd or even? Odd, because if we change the value of our angle to be negative, it changes the overall function to be negative. So sine is odd. Okay, and that was always our test. If we plug in a negative x for whatever our function is and we get the opposite of the original function out, it was odd. If we plugged in a negative x for it plugged a negative x in for it and we got the original function back, it was even. Okay, cosine, is a cosine odd or even? Even, because when we plug a negative u in for our cosine, we still got the original cosine back. So this one's even. Just something you have to memorize exactly. No real way to derive them unless you graph it and look at it. Okay. Tangent, odd or even? Odd. Because when we plug a negative u into tangent, we're going to get the opposite of tangent. So this is an odd, which makes sense thinking about what its graph looks like. Cosecant, odd. So when we plug a negative u in, we get a negative cosecant of u. But secant is going to be even because it works just like the cosine. And finally, cotangent. So the only two evens are cosine and secant. Good. Some of you are still writing. I'll give you a few moments. Yes, sir. Okay. So when we think about a sine, okay, here's our sine, and it starts at 0, 0. Okay, and does that. And then it keeps going backwards, right? Okay. Is that symmetric about the y-axis? No, because it doesn't open up evenly on both sides. Okay. Let's think about the cosine. Cosine starts here, right? What do you think? Is that symmetric about the x-axis? Okay, or the y-axis? Absolutely. Okay. So visually, we can see it. Okay. And then when we talk about the secant, secant looks like this, right? So will that be symmetric about the y-axis? Absolutely. Okay. And it's apparent that if sine is not, then cosecant is not going to be as well. Okay. Now let's think about tangent. Tangent was 0 at 0. At 45 it was 1. So tangent look like this. Is that symmetric about the y-axis? No, symmetric about the origin, isn't it? It's opening evenly about the origin. Okay? Does that make sense? Does that help with the even and odd? Okay, so visualize the graph if you need to. And the only even functions, the only even trig functions are cosine and secant. Okay? All right, so we're going to use our trig identities to figure these things out. Okay, now remember last chapter I said if you don't get it and you don't understand the identities yet, that's okay. We're going to talk about them some more. But if you, and just build your triangle if you need to, figure out what your hypotenuse or your other side is and go from there. Yes, sir. And yep, this is u is just like theta. If you want to write theta instead of u, feel free. Okay, not sure why the textbook author decided to change up. All right, so if cosine of, or cosecant of u is negative 5/3, and the cosine of u is positive. Okay, so first of all, cosecant is 1 over what? A 1 over sine, okay? So it's saying if 1 over the sine is negative, okay, we know all students take classes, right? Okay. If the sine is negative, we know it's not in the first or second quadrant, okay? And if the cosecant is negative, we know it's not in the first or second quadrant, okay? So that means that we're in quadrants 3 or 4, okay? Now, cosine of u is greater than 0, so cosine's positive. So where is sine negative and cosine positive in quadrants 3 or 4? In 4, because the cosine's positive. Okay, so all are positive here, sine's positive here. Cosecant was negative, so we know we have to be in one of these two quadrants. But the cosine is positive here, and that's what they're looking for. So we know that we're in quadrant 4. So that's the first thing I would do every time I see one of these problems, is figure out which quadrant you need to be in. Bless you. Make sense? Did I lose anyone there? Okay, good. So we want to find the value of the 5 other trig functions. Okay? So I'm not comfortable all the time with working with cosecant. I'm more comfortable working with sine. Does anybody have a problem with me saying, okay, well, let's build off of the fact that sine of u is going to be a negative 3/5? We're all good with that? Because the sine is the reciprocal of cosecant, right? And so if I flip over my ratio, keep the sign the same, I have my sine. 1/5 of the way done. Okay. Now let's use the trig identities instead of building the triangle. So our trig identity says sine squared plus cosine squared equals 1. So I'm going to say negative 3/5 squared plus some cosine squared is equal to 1. If I square negative 3/5, what do I get? Yep, negative times negative is positive. 3 squared is 9. 5 squared is 25. Anybody have a problem with me saving a step and saying instead of 1, I'm going to call this 25 over 25? So I'll have a common denominator when I bring that 9/25 to the other side. To save in a step, I could write it one more time. Okay. Now I've got 9/25 added to cosine squared. I want to take it away, subtract it. So cosine squared of u will be 16/25. So what do I have to do to find the cosine of u? Yep, take the square root of both sides, so 4/5. So we have the sine, we have the cosine. What's the reciprocal of cosine? Secant. So what should the secant of u be? Positive, right? We said cosine was going to be positive, so the secant will be positive. Now all that's left to get are tangent and cotangent, right? So how do I find the tangent using identities? Yep, -3/5 over 4/5, right? Because it's the sine of u over cosine u. So the tangent of u will be -3/5 over 4/5. Yep, tangent of u will be -3/5 times 5/4 when I multiply by 5/4 over 5/4 to make the denominator reduce to a 1. So the tangent of u is -3/4. Absolutely. I'm just writing it out to make sure that everybody understands I don't lose anybody. Okay? Yep. Yep. If you know it and you don't need to write that step, feel free. And the last one then, what's the cotangent of u? Reciprocal, so -4/3. Are we all good? Did I lose anybody? You didn't have to use identities this on the test. Okay, so if this was on the test, okay, remember I told you you didn't have to use it, but on the last test, when I said if cosecant is this and cosine equals that, okay, then you would say, okay, this is the hypotenuse over the, and cosecant is 1 over the sine, right? So that would be the opposite. So you could build your triangle. You could say I need to be in this quadrant, okay? If I'm in this quadrant, and my opposite is 3, and my hypotenuse is 5, I can use a squared plus b squared equals c squared and find out this is 4. But now instead of building the triangle, excuse me, I want you to use identities. Yep. And you'll have plenty of time to practice. Uh-huh. Absolutely. All right, we're good with this one? No? Okay, okay, so tangent is known as the sine over the cosine. Okay, that's the reciprocal. So all I did was I took this guy. Yep, and I wrote him over that guy. Yep. So now when we have -3/5 over 4/5, we got a fraction over a fraction. Okay, to clear this fraction, I need to multiply it by 5/4. That way I'll get a 1 down here. But if I multiply the denominator by 5/4, I have to treat the numerator the same way. Yep, and you can multiply it out and call it 15/20ths, or you can just say there's a 5 in common. I'm going to cancel numerator and denominator and get -3/4. Okay? Everybody else okay? And then cotangent, just flip them. Okay? All right, so here we go. So now we want to simplify this. Okay, so if we're simplifying sine squared of x times secant of x minus secant of x. Now we get to go back to good old factoring, but now we're factoring using trig functions. So what do those two have in common? Good question. Looks kind of messy, doesn't it? Yeah, you can think of them as being a variable. Seeing, what did we do in the past when we took the greatest common factor out, right? What's the GCF of these two? Secant of x. So if we take the secant of x out, what's going to be left? Brian, please, Io. Yep. So this was a sine squared times a secant minus a secant of x. So we took the secant of x out. Ladies, please. And we asked ourselves what do we have left? Sine squared minus 1. Okay. Now we can rearrange sine squared plus cosine squared, right? To say, well, sine squared minus 1 means I brought the 1 to this side, right? Everybody good with that? Okay, but I don't like to have, I want this to be all by itself. So if I take away the cosine squared from both sides, this is that identity. The minute I see something with sine squared, I better have an identity to do something with it. Okay, so I said I know one of them has sine squared plus cosine squared as 1. Okay, so let's rearrange sine squared plus cosine squared as 1 to look like this. Okay, and let me start over. Let me make it nice and neat. Hold on, I'll redo it. Yeah, I'm going to take cosine to the other side. Yep, so I have an identity that says sine squared plus cosine squared equals 1, and I want to rearrange it to say sine squared minus 1. Okay. I'm going to bring it, yep, I'm going to set it equal to negative cosine squared because I want to take this 1 to this side, and I want to have the sine squared minus 1 all by itself, so this is going to the other side. So I'll have a sine squared minus 1 is equal to a negative cosine squared. So the minute you see anything squared, sine squared, cosine squared, cotangent squared, or cosecant squared, tangent squared, and secant squared, you can start rearranging your identity. Okay? So this is truly just negative cosine squared of x. Yep, they changed up again. Now it's x's instead of u's or thetas. Okay, using different variables. But what's the secant? 1 over the cosine, reciprocal of cosine, right? So I've got 1 over the cosine times a negative cosine squared of x. These two will cancel, right? And I just have a negative cosine of x. And that's as simple as it will get. Okay. Because I had a cosine squared up here and a cosine to the first down here. So I'll still have a cosine up in the numerator. Garlic bread, I think. Uh-huh. Right. It was squared, so I divided it and I have 1 left. Cosine to the first. Yes, sir. Because this is still kind of messy and I want to get it down to as simple a form as possible. So when I have a reciprocal of this guy, I'm going to put it in the denominator so I can cancel. Okay? Try to get it as small and compact and as simple as possible. It may just simplify to like a secant squared or something like that, but you want to reduce it to as small as possible. Okay. All right. Here's another example. Now we have the tangent of x times the sine of x plus the cosine of x. So we've switched things up again. Now we're using x's for our variable. So what are we going to do? No, that's the tangent of some angle times the sine of that angle plus the cosine of that angle. Needs to be simplified. That would be what I would do. Tangent is the sine of an angle over the cosine of that angle. And that's still being taken times the sine of the angle plus the cosine of the angle is being added on. So I see sine squared over cosine. So far, so good. Okay, but I think we can still simplify this. Because isn't 2 times 5 over 2 times 2 over 13 times 5 the same thing as 2 times 5 all over 13? 2/13 times 5 will get you the same thing as if I take 2 times 5 and put it over 13. 10/13. Let's pick better numbers. Yeah, he asked why I put them together. Let's do this. Isn't 2/4 or 1/2 times 2? That'll get me 1. Isn't that the same as 2 times 2 over 4? Yeah, it's just because they're next to each other, they're multiplied together. So we can put them over the same denominator. Yes, sir. Can we change this to 1? This one? Well, we have to, in order to combine fractions, what do you have to do? Get a common denominator. Okay, so common denominator, we all agree is going to be cosine of x, right? Okay, so if I want to get a common denominator, I'm going to have to multiply this by cosine of x over cosine of x. Multiplying by 1, I'm not changing the actual function or the actual expression. Okay, so now I have sine squared plus cosine squared all over cosine. And all I did was I put them on over the same denominator, sine squared plus cosine squared over cosine. But what's sine squared plus cosine squared? 1. And that's almost as simple as it gets, but what's the reciprocal of cosine? Secant. And it's as simplified as it goes. No dumb questions. Okay, we've got a mess, something that's complex, and we want to get it down to its simplest form. And usually it's going to be just one function, one trig function. Okay, so the goal is to say, what can I use from those identities from the first slide to make this more compact? Okay, so whenever you see a tangent with a sine, good indication is you want to use tangent as sine over cosine. Okay, so we break that down. So we made it more complex to begin with so that we can make it simpler in the end. So sine over cosine times the sine plus the cosine. Now we've at least got them all in the same family, all sines and cosines. Okay, then we say, okay, well, these two are being multiplied together, so I can just write it as sine squared. No big deal there. And it's over cosine. It would be nice if this was also over cosine. So maybe we can combine and simplify. So we put it over cosine. Now it's a cosine squared over cosine. And the sine squared was already over cosine. But now we know another identity. Sine squared plus cosine squared is 1. So we write that just as a simple 1. And now we've made it a whole lot less complex, haven't we? Okay, now instead of 3 things, 2 multiplied together plus something else, we're down to 1 over something. And to make it even simpler, let's find the reciprocal. Yes, sir. The tangent became sine over cosine. Okay. Try to compact things. Just to show that I was basically needing a common denominator. So when you want to add a fraction to a whole number or something, yep, we want to put these on over the same denominator. Okay. All right. Next example. So think of these as puzzles. How can we make them simpler? Right. And yeah, that's typically what I do is I like to work with sine and cosine because I'm most comfortable and familiar with them. There are other identities with tangents and things like that, but sometimes it's nice to get them into the sine and cosine. Now this one may not be so good to do that with it at the moment, right? Because we've got secants and all kinds of other stuff. Good question. Can we cancel anything? What's the secant? 1 over cosine. And we may try this and find out it doesn't work so well. And notice that suddenly they've just decided to give you a t instead of an x or an n or a u or a theta. Okay, so 1 over cosine. What's the tangent? Sine over cosine. Okay, and let's keep going with that thought. Let's make this tangent into sine over cosine. And let's make this into 1 plus, what's the secant the reciprocal of? 1 over cosine. Okay, got a lot more complex to make it easier. Now let's flip this, right? Okay, because if I want to get rid of the denominator, I have to multiply it by its reciprocal. Oops, sorry, cosine over sine. And then cosine over sine. All right, so these guys go away, these guys go away, and I'm left with 1 over the sine. Okay, that's looking a little better. Now let's work with this other side. Before I can even cancel anything, I've got to have a common denominator in that denominator. What's my common denominator here? Cosine. Yep, I'll have to have a cosine t. So I need to multiply this by cosine t over cosine t. Okay, so I'll have a cosine of t plus 1 over cosine of t. Okay. Now, to get rid of that denominator, what am I multiplying it by? right? Okay, and that means I can multiply the top by the same thing. Cancel, 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 cancel. This had already been that, right? And these are gone. So what am I left with? Have I helped myself out? Yep, blue and green. So what happened here was, if I want to do anything with this, I have to have a common denominator, and that would be the cosine of t. So I multiplied the 1 by the cosine of t, and so I'll have a cosine of t plus 1 all over cosine of t. Okay? Now, if I want to get rid of the denominator, because I have a fraction over a fraction, I flip it and multiply by its reciprocal. But if I do that to the denominator, I've got to do it to the numerator as well. Okay? So now we have to have a common denominator again, don't we? Okay? So this is going to be multiplied by cosine of t plus 1 over cosine t plus 1. And this will be multiplied by sine of t over sine of t. When I've done that, I have a cosine of t plus 1 over sine of t times the cosine of t plus 1. And this will be a minus sine squared. All over the same denominator. So this guy came here, cosine t plus 1. Because I had to multiply the bottom and top. This was the original, and this was the original. Okay, so I got a common denominator of cosine t plus 1. So I multiplied top and bottom by that. And then I multiplied top and bottom by sine. Okay. What is 1 minus the sine squared? Yep, cosine squared, right? So this becomes a cosine squared. And I had my original cosine t. And I have a sine times the cosine t plus 1. What do these two have in common? So the GCF is going to be cosine t, right? Cosine, so this is going to be 1 plus cosine. Here's my denominator. Those cancel. And what's the cosine over the sine? Cotangent. I don't like t as a variable. It looks like we're writing cost. Yes. Yep, memorize the identities. They're going to help you. In fact, the more you work with them, the better off you will be. Miss McVeigh was kind enough to share these that she had made for her students. Don't lose these, use them as a bookmark. But the sooner you commit it to memory, the better off you'll be. Okay. All right, assignment. Oh, I've got a couple more things to go through. We got 4 minutes. Let's write the assignment down so that you are ready. It's on the calendar. Should be in your phone if you synced your phone up. Is it an iPhone? We just have to subscribe to the calendar because it just copied it the first time. So go to the sister.com and then pre-calc and select that link, but just copy it, and I'll show you how. Okay. The iCal format. Yep, copy the link. And then once the link's been copied, go to settings and then go to your settings. And then calendars, contacts, and whatever it is. And then add new calendar, add account, other. And then choose a subscribe calendar. And then paste that link. Oops, I'm sorry. And then say save. And then say, yep. And good. Hit next, yep. And save. Just go ahead and see in the calendar if it's there. Okay. All right. So we'll come back and talk about this, but do as much of your assignment as you can, okay? I'm anticipating, I don't want to jinx it, but I'm anticipating snow day tomorrow. So on Wednesday, we'll come back and finish the rest of this, but do as much as you can. Okay?